Excuse me, sir. Your voice is not audible, sir. Sir, your voice is not audible, sir. Hello, sir. Hello. Hello. Hello, sir. Your voice is not audible, sir. Hello.
Hello, hello. Voice is not clear actually.
Hello, can you hear me now? Okay, thank you. I'm really sorry. I hope you could still follow, but okay, since I have written the notes here, it will be easier to explain.
Actually, hello. Actually,
Yeah.
from the starting, what you have written, just we
Yeah.
are seeing. But
Okay.
if it is better if you start again, the repeat the whole portion again, because
Yeah, I am. Yeah,
it is
it's
now at
okay.
a one-way communication. You are writing, but we are just seeing that we can't
Yeah,
following
it's
it
okay. It's
actually.
okay. I understand. I apologize for it. I wasn't checking the.
Firstly, sir, I am thinking that my side is problem. Then I am checking my
No,
all
it's okay.
apps. That's
It is
okay.
fine. I got messages from
That is
multiple people.
now it is clear. Sir, I am
Okay.
requesting you to please from starting you
Yeah,
just.
I'll just explain this once again.
Mm, mm.
So okay, so for details of this DFT's DS spreading mechanism, you can review lecture 30, lecture 42. So this is in lecture 42. But I just provided quick overview for the problem purpose. So in this technique, what you are doing is you are sending the signals instead of sending the symbols, you are kind of shaping it with this pulse shaping pulse shaping signal or pulse shaping filter. So what does this do? What this does is that so this has a peculiar structure, which is you are using these chips or this kind of you are using this basic modulating signal, which is GC of t, which in time domain is just a rectangular pulse. So this is something like this, 1 by root over Ts from 0 to Tc. So we are familiar with this kind of rectangular signal, right? And then we are kind of multiplying these signals and shifting them. You can see that this is like um, a bunch of signals, one after the other in time domain, shifted by uh, these values, QTC. And we are multiplying this chip function or a spreading sequence with a length capital Q. So if you see that, and all of these spreading sequence have value 1, or like some plus minus 1, some value. So essentially, what happens here is that if we have our original g of f, which is this function, so if you take Fourier transform of this, you will get capital G of f, and so that is directly related with the symbol time. So this is nothing but like if you have to write g of t, this is nothing but this function, right? 0 to ts with magnitude with magnitude 1 by root over ts, something like this. Right. So essentially, if we break this function into many parts, we get each of these tip functions, which is gc t minus qtc, and then we are adding them up. So like it is essentially we are slicing this gt function into these small chips, and then we are adding them up. So it's just mathematical trick in a way. And so
Sir, please repeat this portion again. Please repeat this.
so so this is like um, your G of t is the modulating pulse shaping technique tool that you're using. So, so if you look at it from the other way, that if G of t is a rectangular function from 0 to Ts, what you are doing here is you are breaking it into many parts, which are each from 0 to Tc. Like, well, okay, Gc of t is from 0 to Tc. So that happens. But then if you have Gc of t minus tc, for example, which happens when you have q is equal to 1. So then you are shifting this from TC to 2TC. And so similarly, if you add them all, you will get the whole G of T, right? And so the crux of it is, if you take G of T and take its Fourier transform, the actual pulse shaping filter, you will get something like this, right? The magnitude will be Ts and the crossing point will be 1 by Ts, right? So this you have to identify. But then, as I show here, that for the smaller function, for the smaller chips, that is GC of T, since this is the formula, so rectangular function again, rectangular function in Fourier domain becomes sinc function. And if you take magnitude of that, then you get this TC squared by TS sinc squared FTC. And since the symbol time and the chip time are related by this factor Q, which is the spreading sequence length, then you can just substitute the chip duration. And what you see here is, from this G of F to this GC of F, that the magnitude is reduced by factor of Q squared.
Sir, 1 minute. What is the Q factor?
Q is the length of the chip sequence. So, so this is a choice of the pulse shaping filter here, that I'm using capital Q number of number of chips. So this is Q. This is Q. This what comes in the summation. So I'm just shifting this rectangular pulse Q times and then adding them. So then what happens essentially is, if you do the math, two things happen. The magnitude falls, the magnitude declines by a factor of Q square, and then the first crossing point, so sinc function has its minimum at value 1. So first crossing point, instead of 1 by Ts, it becomes 1 by Tc now. And so 1 by Tc is Q by Ts, right? Because Ts is equal to QTC. So this point shifts by a factor of Q. So first part which I solved here in this question, what I'm asking you is to, okay, you are told that the symbol weight is 125 kilobaud, and you are using DFT spread modulator, and chip duration is 2 microseconds. And you are asked to draw this. So first part is, first you have to draw the basic without spreading. If you have to design a modulator function here, what will that look like? So without spreading, the modulator function is exactly like this. So this is how you do the modulation. Symbol, so it is a rectangular function of the size symbol duration, right? So if you forget spreading and all, like if we are not doing all these spreading techniques, then what we do is we take a rectangular filter, right, from 0 to Ts, and magnitude is 1, let's say. So this is how you do modulation. Now, so that is how this will look like. So essentially, we have to find out the value of Ts here, and we are given in the question Rs, which is 125 kilobaud. So if you take Ts, the symbol duration is 1 by Rs. So that is, if you solve it, you will get 8 microseconds, right? And the first crossing point is, so after this, it is just some more values, not too concerned about all of that. But first crossing, so magnitude is 8, this amplitude is 8, which is equal to Ts. And first crossing point is 1 by Ts, which is 1 by 8. And if you invert microsecond, you'll get megahertz. So 1 by 8 megahertz. So you can write this as 0.125. The frequency is typically written in megahertz. Right. So this is GF without spreading. And now if you are asked, okay, so essentially let's draw mod VC of F whole square with spreading. So what happens with spreading? So here just one unknown needs to be figured out. Let us finish. So if I need to draw this, so this is mod GP of f whole square versus f. So I need to find out the magnitude and the first crossing point, right? And it will look something like this. Okay. Or maybe not exactly. So magnitude and first crossing point. So first, so I need to find out essentially. So I know that the chip duration here is 2 microseconds. See, it's given in the question. Chip duration is 2 microseconds. And symbol duration I have already derived to be 8 microseconds. So what that means that the Q factor is nothing but TS by TC, which is 8 by 2, which is 4. Right? So, so the magnitude is 8 by 4 square. It gets divided by 4 square. And the first crossing point gets multiplied by 4. So then this becomes 0.5, and this also comes out to be 0.5, I think. 0.5 megahertz. So this is in megahertz. 0.5 megahertz, and that is just magnitude. Not too concerned about the unit. So I hope this is clear, because I just discussed the theory that you have to find out Q essentially, and then your amplitude falls by Q square, and your first crossing point is multiplied by Q. So Q, we found out Q is this. This is the factor that is chosen. Q is TS by TC. Symbol time by chip time. So this is just one small, actually, is not the more important topic, but this is there in this week's assignment. So we just covered. Is this clear now?
Now it is clear.
Okay. Okay. So, okay. So now, now we can come to the more important topic, which is capacity, power allocation, etc. All of these things. Okay. So, so you are told that maybe first time. Somebody joined in. Let me get. Okay, so let's say you're told that you have a system where you have one transmit antenna, and let's say 4 receive antennas, right? You're told this, and let's say transmit your, like in this system there is some noise, and noise is IID Gaussian. So all noise is IID Gaussian with this distribution 0, n naught IID, right? Independent and identically distributed, and channel is constant. Let's say so AWGN channel. So AWGN channel. I hope we know what AWGN channel is, but just to clarify, AWGN is it's something called additive why this term might be used introduced Gaussian noise. So this is a very simple channel with no fading. So what you have here is just your signal X, which comes into this channel, and nothing happens at this channel other than this addition of a noise, which is Gaussian, from, for example, 0, n0. So some noise is added, and then you get your output. So we are not considering fading and all of this. This is a very simple AWGN channel. So in AWGN channel, typically your channel, your output looks like something like this, which means that your channel, which is actually coming here, your channel H is equal to 1. So essentially it's just a unit channel. And so you are told that, so that's AWGN channel, that is for, so this is for single input, single output, CISO. But here you are given this single input, 1 TX and multiple RX. So CMO, or single input, multiple output case. So in that case, it will be just this Y equal to some 1 vector times X plus N vector, right? So that is how, so this is CMO, single input, multiple output channel. Here 1 vector is nothing but vector of ones, 1, 1, 1, 1 transpose, right? And these are all, and noise vector is just, each of these terms is this thing. It's again 4 cross 1. So this is your, at your RX you have 4 antennas, so you receive a 4 cross 1 symbol. So these are all 4 cross 1. Right? And each of these noise terms are, each of the 4 noise terms are IID, independent and identically distributed complex number with noise mean as that, right? So I just wrote it in vector notation. And so you are asked what is the, so in another thing that I provided is transmit power constraint is P. So at most you can transmit with power P. So so you are asked what is the capacity of the channel. So what is the capacity of AWGN channel? So let us quickly do the derivation for this, right? Essentially, what you can do is, you know that you ultimately want to combine all of these 4 signals, right? So you will have to, because ultimately you are sending this, just this one symbol, which is X. So your received symbol will also be some scalar, R. What you can do is you can just combine this Y, right? Combine this Y with this 1 transpose vector. So this is like, so if you just expand Y, so it will be 1 transpose times 1 times X plus 1 transpose times N. I like to use vector notation, that's why I'm showing it this way, right? So this is your received symbol, R. At the receiver end, you're just adding up signals from all of the 4 antennas. So 1 transpose 1. So this is like vector 4 cross 1 vector. So this will ultimately add up to L. Like this will ultimately add up to 4, right? Because it's like 1 row vector, 1 column vector. So it will just add up to 4. 4x plus this essentially summation over ni, I equal to 1 to 4. So this will give you n1 plus n2 plus n3 plus n4. Because your n vector is this thing, right? N vector is something like n1, n2, n4. 4 antennas, so 4 noise terms. And if you do one transpose over this, then you will just add up all this. Similarly, your one vector was also this thing. One vector, you also write n vector property. 4 cross 1, n vector is n1, n2, n3, n4, whole thing transpose. Right? So now your signal power is, and you're told that the transmit power constant, which is this thing, is equal to P. This is your symbol power. So what is your capacity? So first see what is the SNR here. SNR is signal power squared. So it will be 4 squared times P divided by, now these are 4 noise terms and each of these terms is of magnitude N naught. We are told in each of the noise terms have variance N naught. So if you are taking, and these are all independent. So this is like 4 terms each with magnitude mod Ni squared, which is N naught. So this will be 4 times N naught. So this will give me 4 times P by N naught. And so my capacity is log of normalized capacity, let's say. Let's forget about bandwidth for now. So this is log of 1 plus SNR. So 4 times P by N naught. So I hope everybody could follow this. So this is how you derive capacity for multiple antenna system. I took the value. I took the specific value 4, but you can pick any value. So first, depending on the question. I hope this was clear. Moving on, some questions are straight from the lecture. You can just see the lecture and just solve them and like answer them. So I'm not focusing on those questions because otherwise we'll run out of time. So this was one kind of quick derivation that I thought I'll show. I hope this is clear, right? If there are any doubts, please let me know. Okay. Now we can come to the more kind of complicated topics. So this was one type of pressure. So you are given, let's say you are given like a single tap channel or whatever. You are given a single tap channel. So which essentially means that it is not frequency selective. So you don't need to bother. Single tap channel and bandwidth is, let's say, 20 megahertz. Okay. This is typical for 5G. And you are given some SNR characteristics. SNR characteristics. What kind of SNR characteristics? That it can have SNR of this gamma 1 equal to 0.5 with probability P1 equal to some like P1 equal to, let's say 30% of the time it has SNR 0.5, right? Gamma 2, another like maybe another 30% of the time it has SNR 2, let's say, right? And gamma 3, another, then the rest of the 40, let's say rest of the 40% of the time, it has SNR some 5, something like this. So this is your SNR profile. You have a channel with this kind of an SNR profile, right? And you are asked, okay, find the ergodic capacity. Let's call it. So, how do we calculate this? So for ergodic capacity, C is equal to bandwidth times. So ergodic capacity is nothing but expectation. Let's take the bandwidth out of the expectation. Bandwidth times expectation over log of 1 plus SNR. Right? So this is your expression for ergodic capacity. You just have to calculate this. This is a very mechanical question. So this will be B times summation over for all of these three possible SNRs, right? I equal to 1 to 3. You will take the expectation means you will take the value and multiply it with probability and then add it up. It will be Pi log of 1 plus gamma I. So Pi's are known, gamma I's are known, like gamma I and Pi corresponding, you know, and you know B. So you can just calculate and tell me the answer. So I'm not going to spend too much like time. Let me try. I have my calculator here. Can somebody do the calculation and tell me quickly? So I'm somewhat getting capacity to be 33.7 megahertz. Sorry, not megahertz, like Mbps. Bandwidth is in megahertz. So you can just verify. So this was also there something similar before in the previous assignment as well. Now for this same channel, you are asked to find something known as. So this is with the current SNR distribution, and you are not doing any kind of fancy power allocation. You're not trying to do anything. But now let's say you want to do optimal power allocation. So you want to do different power allocation for each SNR state. So this is like, so you have some average transmit power allocation constant, which is P bar. So normalizing by that, constraint is P bar. So this is what your average power should be. If you normalize by that, what is the power that you will use to transmit with each SNR state? So let's say you have to do it in an optimal way. So how do we solve this kind of question? So this is solved by using the water filling algorithm. It is there in the lectures, lectures 43, 44, I believe. 44. And even later. So this is a very fundamental algorithm. And so I'm not going into the theory for now. I think it's better to go over it yourself. But essentially, it's a long derivation, and then see that for um for your optimal allocation, you need to essentially solve this equation. So P of gamma I is nothing but 1 by gamma naught minus 1 by gamma I plus times the transmit power. So this is the formula, and the plus denotes max of this, whatever this quantity is, and 0. You cannot have a negative power allocation. So essentially what we do is we assume that this is positive. We assume that the max of this quantity with 0 is this quantity itself, and then we try to solve. And sorry, this is multiplied. This is normalized by the temperature. This is multiplied by the probability that this state occurs, right? Or PI. So in my notation, PI. So essentially, what we are trying to do is we try to assume that this will be positive for all the channel states. This will be positive, and then we solve. And then if we don't find our assumption, then we have to validate the assumption also. If our assumption is not valid, then we change tactics, and then we start rejecting some channels. So while solving, we'll actually see if that indeed is the case. So in this case, let us see. Summation I equal to 1 to 3. So what happens is, now if I sum over all three, this thing, P of gamma I over P bar, I should be getting 1. I should be getting 1 value, right? Sorry, so this is the allocation, and then if I sum over all three, I should be getting 1. And sorry, let's do this here. Because I cannot allocate more than 1 unit power, like if I normalize everything. So, so then I just have to, like, so I have to sum over all three. I equal to 1 to 3. 1 by gamma naught minus 1 by gamma I pi equal to 1. So over here, gamma I is known and pi is known. I have to solve for gamma naught. This is the unknown. So can somebody solve and tell me what gamma naught will be? So I have to solve for gamma naught. So if we just break it up, 1 by gamma naught, summation over all pi is 1. So if I take the first term out, then it will be just 1 by gamma naught. And on the right hand side, I'll have 1 plus this thing. Summation I equal to 1 to 3. I think pi by pi divided by gamma I. So what will this come out to be? pi PIs are 0.3, 0.3 and 0.4, 0.5, 2 and 5, right? So 0.3, 0.3, 0.4, this is 0.5, 2 and 5, right? 0.5, 2 and 5. So 1 by gamma naught equal to 1 plus how much? 0.6 plus 0.15 plus. I need this calculation particularly because I just need to check if some property holds. So this comes out to be 1.83, right? And now let us find out let us check these 1 by gamma is. So 1 by gamma 1 equal to 1 by gamma 1 is 2. 1 by gamma 1 is 2. 1 by gamma 2 is 1 by gamma 2 is, I'm just calculating all of them, but I'll show you which one is important. 0.5 because gamma 2 is 2 and 1 by gamma 3 is 0.2, right? Gamma 3 is 0.2. So you can see that 1 by gamma naught is less than 1 by gamma 1. Therefore, assumption is wrong. Why? Because we had assumed while writing this formula itself that all of these terms are positive. So we had assumed that 1 by gamma naught minus 1 by gamma 1 times some probability which is greater than 0. But anyway, main thing is we had assumed that this will be greater than 0, which is why we had, like when we solve for max of some quantity comma 0, we get that quantity itself when that is greater than 0. Right? So we had assumed this thing that 1 by gamma naught minus 1 by gamma 1 is greater than 0, but clearly it turns out to be less than 0. So assumption is wrong. So we have to essentially, so if we look at this, we have three channel states. This is the strongest channel. So this is the strongest channel. This is second strongest, but this is the weakest. So the key thing which we first need to check with the weakest channel. So that is what I did first. With the weakest channel, I can see that my like kind of overall allocation or this gamma naught term is not sufficient. So the SNR allocation is not sufficient. Power allocation is not sufficient. So in that case, we'll have to just leave or let go of this weakest channel. That I am not being able to allocate sufficient power in this case for the weakest channel. So for sufficient transmission, so I'll have to ignore the weakest channel, right? So essentially, the power allocated P of gamma 1 by P bar is 0, is equal to 0. So this is for one channel we have solved the problem that we cannot allocate any power to this because my assumption is falsified, and so I'll have to assume that 0 holds, right? According to water-filling algorithm, I'll have to assume that 0 holds, and so I don't allocate any power. Now let us solve for the other two. For the second and third channel, how much power we can allocate. So for that, so 1 by gamma naught minus 1 by gamma I Pi equal to 1 for I equal to 2 to 3. Right? We are ignoring the first channel state completely. And over here, if we do the solution, we will get something like 1 by gamma naught equal to 1 plus P2 by gamma 2 plus P3 by gamma 3. So this will be 1 plus 0.3 by 2 plus 0.4 by 5. Maybe do 5. Yeah, P2 by gamma 2, P3 by gamma 3. So 0.3 by 2, 0.4 by 5. And so this will give me how much? Point 0.23, so it will be 1. Fine. So now I can compute P of actually in the allocation part, I am not multiplying Pi. My bad, this is incorrect. But in the summation part, actually, I have to sum it with Pi, right? Why? Because the probability that this state gamma I occurs, so the probability that gamma equal to gamma I is pi. So when doing this summation, when I'm applying this average power constraint, I need to multiply the pi. So anyway, uh, p of uh, p of gamma 1 is already solved. P of gamma 2 by p bar is now how much? 1 by gamma 0 minus 1 by gamma 2. So this comes out to be gamma naught is known 1.23 and gamma 2 is 2. So 1 by 1.23 minus half. That's how much? Minus half. This comes out to be 0.313, right? And similarly, P of gamma 3 by P bar equal to 1 by gamma naught minus 1 by, and this is greater than 0, so our assumption is valid. 1 by gamma naught minus 1 by gamma 3, which is 1 by 1.23 minus 1 by 5. So, minus 0.2 comes out to be 0.613. Oh, okay, my bad. Calculation error. So this is 1.23 minus half. And this is 1.23 minus, yeah. So calculation error again, because 1 by gamma naught is 1.23. So this is 0.73. Right? Did I make some calculation in it? Something. $1.03. Yeah. Okay. Yeah. That is fine. One second. Regarding this GF without spreading and GF with spreading, I have already discussed, I think, uh, before, probably before you join the call. So you can go over the video later. I've already discussed this. If there is some time at the end, I will discuss upon it again. Otherwise, you can go over the video. Fine. So is this water filling part clear? Yes. Because the values will change, like any value you can change. I just poked up values over here, but the concept is important. So again, just to recap, we are assuming that this formula holds with uh, with positivity, that we are allocating some power to all channels. Then we see if we can do that. So what we can see here is we try to do that, and this is the value we get, and we can check that our assumption is wrong. That for the weaker channel, we are actually allocating some negative power, which we cannot do. So we rectify our assumption, we allocate zero power to the weakest channel, and now for the other two channels, these are the values of the power allocation. Now, in your question, you might be asked to report this in dB or whatever. So you can do it. So you can just report in dB or in decimal, whatever is asked. Now with this, so we solved for optimal power allocation. Now what is the so, so now you are asked what is the maximum capacity. that you can do. You are asked for the maximum capacity. So maximum capacity is essentially whatever capacity you achieve with water filling, right? Because water filling algorithm essentially maximizes capacity. So you already have the solution for maximum capacity. You just have to put it in, right? So for capacity, C is equal to B times it is ergodic capacity because you have 3 channel states. So for each channel state, probability of that channel state Pi times log of 1 plus this thing, right? The power that you are allocating, this normalized power allocation times SNR. P of gamma I by P bar. Now we know that for first channel zero power, we are allocating zero power, so that actually doesn't contribute. If you put zero here, the capacity log of 1 is 0, so that doesn't contribute. So for the other two terms, you are told that it's a 20 megahertz channel, so we have that value. We have the value of B. For the other two terms, what can happen? So if you just substitute this 20, and the answer will come in Mbps because it's megahertz. So you will have Pi, the second state probability was 0.3 times the allocation for second channel. Third state is 0.4 times the allocation for third channel. So 0.3 times log of 1 plus, what is the second channel allocation? 0.73. So 0.73 times gamma I. Gamma I is 2, right? Gamma I was 2. Gamma for second channel was 2, and for third channel it is 5. Plus, so plus 0.5 times log of Pi times log of 1 plus 1.03 into 5. So this is simple calculation. You can just put in and get the value. I'm not doing it. Any difficulty with this question? Okay, you can just solve. I'm not solving it. Now you are asked that so now you are told that CSIT, CS for the same channel, CSIT is not available. What does this mean? So this typically means that you have some statistical knowledge at the transmitter. You have some statistical knowledge of the channel, but not the exact knowledge. So you don't know the current state of the channel, which means that you cannot do water filling. So CSIT is not available, then you essentially you cannot do water filling. Why is this? Because to be able to do water filling, you need to know what state the channel actually is. Like if you know the state, the channel is in state gamma 2, is in state 2, then you will do this allocation 1 by gamma naught minus 1 by gamma 2, and then you will achieve your optimal capacity, right? So if you don't know which state the channel is in, then you cannot do water filling. So you have to kind of guess how the channel might behave, and then do your transmission. Okay. My bad, screen sharing got discontinued. Just a second.
Sir, why this CSIT is not available here?
It's just you're given this problem. Like, not always, it is not always practical that you will have channel state information. It is not practical. You might not be able to measure it at the transmitter in real time. Like, you might have some notions, some statistical understanding that okay, the channel on average it behaves like this, or this is the fluctuation. But in real life, you might not have like the exact channel knowledge at that very moment. So that is why this is some practical consideration that you need to take care of. Okay. So
So, sir,
so
due
your
to that, sir, can I ask?
yeah.
Yeah, so you have written it, water filling is not applicable.
Yeah, you cannot use water filling algorithm. Uh, you cannot use water filling algorithm. I kind of tried to explain why. I'll just explain again. See, for water filling, all of this mathematics is fine. You solve, you get the answers, and all that is fine. But when you are actually doing the power allocation, you need to know that the channel is in a particular state, right? You need to know that, okay, if the channel is now in state gamma 1, I'll not allocate any power. If the channel is now in state gamma 2, I'll allocate 0.73 power. If the channel is now in state gamma 3, I'll allocate 1.03 power. So you need to know, and only if you know that you can do water filling. So yeah, that is the thing. If you don't know, you cannot do much.
Okay, sir.
So if you, I hope you understood, right? So now your question is, now you cannot do water filling. So that is, unfortunately, you cannot do. What is the best you can do? So that is, you are asked what is the capacity with outage. So statistically, you know this. You know that this is the statistical behavior of the channel. But what you don't know is when you don't know that in the current time instant, you don't know whether it is gamma 1, gamma 2, or gamma 3. So worst case, what you can do is, you can, like, if you want to be absolutely safe and if you don't want any outage, then you can assume that worst case channel is gamma 1, and so you don't want to allow for any outage. So you will assume worst case and transmit according to that, right? So what is the capacity you will get in that case? So case 1, so just follow the steps that I'm showing, and then you'll understand why I'm doing it. So case 1, you are assuming no outage. No outage. So you will assume that channel is in worst case, right? So channel is then always gamma 1. So you'll take this as worst case. Worst case. So in worst case, capacity will then be B times log of, so B is 20 megahertz times log of 1 plus gamma 1, which was 0.5, right? Gamma 1 was 0.5, and gamma 1 was 0.5. So you will assume that worst case, this is what I have. And so the best rate, so my safe estimate of capacity will be this 20 log 10, 1 plus 0.5 units and Mbps. So can somebody calculate and tell me? It's very simple. 1.5 divided by log. I need these calculations also because I need to compare a few cases. And this is case 1, there will be a few more cases. So this comes out to be, somebody can verify, it would be great. It comes out to be 11.7 Mbps. So I'm denoting it as C1. Let's say. First case, I am assuming worst case channel, and this is the capacity that I can achieve. Right. Second case is we take some risk. We say that okay, let's forget about the worst case channel. So like let's consider 0.3 outage essentially, because worst case channel probability was 0.3. So you're just saying that let us just forget about the worst channel. So if the channel is in its worst condition, we will not be able to meet the capacity and there will be outage, and we are okay with it. Let's say. So we'll only be able to serve the user when it is either in gamma 2 or gamma 3. So here you can see that so you will only serve the user when it is in the second and third state, and gamma 2 is the lower one. So let us assume in this case, like the average case maybe, that the channel is always gamma 2, right? It's either gamma 2. So when it is not in outage, it is always gamma 2, right? Average case. So what will be the capacity in this case? You have to multiply the outage probability, which is, you have to kind of multiply this factor, because 30% of the time, then you are not transmitting. So that is how you are designing your system, that you won't be transmitting if you are you won't be transmitting, or it's not like you won't be transmitting, it's more like at the receiver end you won't be receiving if your signal is, if your received SNR is gamma 1. You are just like leaving it for the time being. So 30% of the time your capacity is 0. The rest 70% of the time your capacity is again B times log of 1 plus gamma 2, which is 2. So this comes out to be how much? Will somebody calculate and tell me? Log of 1 plus 2. So this comes out to my calculation. If somebody can verify, it would be great. It comes out to be 22.2 Mbps. Right? So this is one value. Third is we will only serve when the channel is, so we'll say always. So we'll assume best case, right? That the channel is always and gamma 3 or like. So if it's not gamma 3, if it's not at this level, we will not even receive the signal. We'll just, if the detected SNR is less than this gamma 3 level, we'll just reject everything. So which means that 60% of the time, 0.3 plus 0.3, 0.6, we'll be just rejecting the signal. 40% of time we'll be accepting. So this is then 0.6 is the outage probability. So if we solve, then this means that with 60% outage probability, we are solving. So we have 60% is outage. So the rest 40%, let's see what rate can be obtained. And gamma 3 was 5, I believe. Right? Yeah, gamma 3 was 5. So can somebody do the calculation and so this, somebody please verify. Times 20. Yes. Right. So I'm getting this to be 20.7 Mbps. Right. So now let us compare these three values, right? We have, these are all the possibilities that we can have, right? We can either assume worst rate and transmit according to that, or we can assume the average rate, forget the worst case, transmit according to that, or we can assume that best that only the best case scenario will be there, and we neglect the bottom two scenarios, and then we transfer according to them. So whichever is the maximum, that will be the optimal strategy, right? So this is maximum. So C2 is maximum. So um, so essentially case2 is maximum, and so capacity is, this is the capacity that we'll get. This is the best that we can do. So we can get 22.2 Mbps capacity. So this is without channel state information, and this was the ergodic capacity. And anyway, let us find optimal capacity. If somebody had calculated this, then we would have gotten. Actually, let's just quickly do it, because I want to show something. 1 plus. So this is the capacity with water filling algorithm, and it should be higher. It should be like higher than everything else. Plus so this comes out to be roughly almost 34 Mbps. 33.99, almost 34 Mbps. So you can see that ergodic capacity is lower than uh, this capacity obtained with channel state information or with water filling. So this is always the highest on the optimum, and without channel state information, this is much lower. So if you don't have channel state information, then we can achieve much lower capacity. And now there comes a fourth method, which is channel inversion. Channel inversion, right? So essentially, we know that we know the channel, and we just invert it. We just like during transmission, we just multiply the signal, precode the signal with something like 1 by gamma. So you can check the lectures for derivation, but essentially for channel inversion, your capacity, so you're using channel inversion technique, and you want to find out capacity, right? Okay. So capacity with channel inversion is actually given by this formula. So bandwidth times log of 1 plus sigma, some value sigma, where this sigma is so it is the expected value of the inverse of the channel. So it's kind of like that's how it comes, because if you are multiplying with 1 by gamma and sending, then like your gain becomes essentially something like this. So you are just inverting the capacity, the channel. So this is your capacity with channel inversion. So let us compute this thing, expected value of 1 by gamma. So we know that this is the channel state, right? Gamma 1 P1, gamma 2 P2, gamma 3 P3. So just memorize the values. It's 0.3 times 1 by 0.5 plus 0.3 times half plus 0.4 times 1 by 5. Right? So this is the value. 0.5, 2, and 5. So if somebody can calculate this, then C is equal to 20 times log 2 of 1 plus whatever this is, equal to Let's quickly do this calculation. 0.3 divided by 0.5 plus. So this channel inversion technique is sometimes used for equalization purpose, so that different channels don't have different uh, gains and like more or less equal. So I'm getting the value 0.83. Just substituting this here. And sorry, so this is expected value of 1 by gamma, and sigma is 1 by expected value 1 by gamma. So this is 1 by 0.83. Right? So yeah. So I'm just putting this value over here. So sigma is expected value of 1 by gamma. So can somebody calculate and tell me? Let me try myself. I'm getting to be somewhat like 22.8 Mbps. So this is also very low. If you compare with this water filling, 34 Mbps, 22.8 Mbps is pretty low, right? And I hope I didn't make any calculation error. So now, so this is a complete channel inversion capacity where you are considering all the channels. Now there is also something called truncated channel inversion capacity. Truncated channel inversion technique or truncated channel inversion capacity. So when do you do that? So in truncated channel inversion, what you do is you ignore the ignore some of the channels and invert according to the remaining channels. Right? So so this sigma value is essentially 1 by 0.83. One second. The sigma value here was actually 1.2205, right? Because expected value of 1 by gamma was 6.8. So 1 by this is this. Anyway, for truncated channel inversion, let us again try all three cases, right? So let's say one case is this. One case is we already know that if we are considering all of the three channels, then we have already computed the truncated, then the channel inversion. Now if you truncate it, let's say again case two, let's say case one is already considered. Case two is like this again uh, 0.3 outage case where you are neglecting the weakest channel. So you are assuming it's always gamma 2. But this is the average case, right? So in this case, or actually we shouldn't write it this way. So case 2 is when there is 0.3 outage probability. So you are ignoring the first case. Like you will be ignoring your receive signal when gamma is equal to gamma 1, the weakest channel. And you'll only consider the second and third case, right? So in that case, what will be your truncated channel inversion capacity? It will be uh, one by this formula still says the same, 1 by expected value of 1 by gamma, but it's not a full expectation, it's some kind of truncated expectation. What is this expectation? Over 1 by gamma. So you'll ignore the first, the weakest channel, you'll ignore gamma 1. You'll ignore gamma 1, you'll just take second and third, 2 and 5. So for 2, the probability is, so for channel gamma 2, probability was 0.3, and plus 1 by 5 into 0.4. So whatever this gives. This gives me 0.23, right? And if you take inverse of 0.23, and then so your capacity in this case C2, let's say, it will be uh, firstly 1 minus outage probability, which is 0.3, 1 minus outage probability 0.3. So whenever it's not in outage, then it will have this capacity, right? This log V times log of 1 plus 1 by expected value of gamma, which is 0.23. So we can quickly calculate this. Plus 1 into 20 into 0.7. It's coming out to be some 33.86, 33.87 Mbps. So this is pretty good, right? Let's also consider the third case, case 3, which is 0.6 outage case. So I'm just neglecting the first and the second channel states now. It's only the best case and best channel I'm considering. So again, so in that case, my expected value of 1 by gamma will be, just a second. Let me verify something real quick. Just give me a moment. Yeah. I'm doing it correctly. Fine. So, so let's now take the like uh, 0.6 outage case that we just neglect everything. So again, sigma equal to 1 by some kind of truncated expectation of 1 by gamma, where truncated value here in this case is, let's just neglect the bottom two channels, the worst channels, and only best channel is considered. So that is SNR of 5.4. So this is 0.08, right? 0.4 divided by 5, 0.08. And so the capacity C3 in this case becomes 1 minus 0.6 times the bandwidth times log of 1 plus 1 divided by 0.08. Let's see what this comes out to be. Hmm. So this comes out to be roughly 30.04 Mbps. So out of these three situations, in the first case, when we are considering inversion over all the channels, so we have 22.8 Mbps. Second case is 33.87. Third is 30.04. So we pick the second case because it has the highest value. And so we can see that with truncation, we can obtain a pretty good value, 33.87. That is very close to water filling allocation. Water filling is almost 34. So almost 34. It's close to 34. So the channel inversion, while channel inversion, maybe complete channel inversion is a bad idea, but truncated channel inversion can give pretty good capacity values. So I hope this is clear. Any doubts regarding this problem? So this was actually the crux, the main part of this week's assignment. So yeah, any doubts, because this is the most important.
Sir,
Yeah.
sir, this channel inversion means what exactly we are doing, sir?
In channel inversion, you just just give me a second. I'll confirm from the shell. So in channel inversion, what you are like, it's taught in different ways. I'll just refer to the notes once. Mm, just give me a second. So okay, in channel inversion, as I was saying, right, that so channel inversion can also only happen if you have channel state information. So you CSIT, like you have channel state information at transmitter. So that is what CSIT means, that you have channel state information. I'll just write it down for reference. Channel state information at transmitter. So only then you can do these things like water filling and channel inversion. What you do in channel inversion is you want the channel to look like AWGN channel. So you just want to remove the gain part from them. So then how will you do that? You will just allocate power accordingly, right? So you will allocate this thing, you will allocate power like this, something like sigma by gamma. Because then if you multiply this with gain, what will happen is sigma by gamma times gamma will cancel. Gamma and gamma will cancel out. And so essentially when you do for your SNR, you do log of 1 plus SNR. So so SNR will be power times the transmit power times the system SNR. So gamma and gamma will cancel. So effectively, your channel will have SNR sigma, and your capacity will be D times log of 1 plus sigma, right? Now, what is this? Now, how do we choose this sigma? That is again, that is solved by using power constraint. Power constraint. What is the power constraint? That my average power allocation has to be P bar, or this integration of P of gamma over this over the PDF of gamma. This has to be equal to P bar, right? So you have to solve for this. If you solve for this, you see that sigma sigma becomes constant, it comes out. And so if you just rearrange it, this is what you get, right? So then, so this is what you have to solve. So you can just quickly show. Sigma comes out as a constant. So sigma is a constant, and then what you have is 1 by gamma, f of gamma, d gamma equal to 1. And so if you solve, so this integration is nothing but expectation over 1 by gamma. So your sigma becomes 1 by expectation over 1 by gamma. Okay, I hope this is clear. That so this is channel inversion technique where you know the channel information and you are just essentially cancelling the channel out by just inverting, like a transmission time, you are just in multiplying it by sigma by gamma, and sigma value is known. Is this clear now? So, so yeah, your channel capacity will then become C equal to mu log of conversion. Is it clear? Again, regarding your question, Deola, that I have discussed this G of F without spreading and with spreading earlier in the lecture. Let me see. I actually still have one more topic, small topic to cover. I don't think I'll be getting time to go over it again. So you can review it from the notes and the YouTube video later. I've already covered it in detail.
Okay. Okay.
So that is regarding the spread spectrum discussion. But yeah, is this channel inversion thing clear? Okay. Anand, I believe, right? I hope this is clear. So then, so this is what we do in channel inversion. And so what I discussed in the problem is that if you do channel inversion for all of the channels, then this is the capacity we'll get. If you make a decision to just neglect the weakest channel, the worst channel state, and you do channel inversion for the other two, then this is the capacity we'll get 33.87. And then third case, if you just take the strongest channel, then so these are all calculations that you can do and very quick. And then you can compare essentially between various techniques. Okay. So if this part was clear, let me quickly cover something else. Is there some minor question? Let me just check. No, all this is fine. All this is fine. Let me cover this last kind of question. So this was one very big, like it's like a single problem with many sub problems, and so that is so now let's say you have a kind of question. This is actually very simple. So you have two users. So let's say user one and user two, which is two mobile phones, and it's transmitting to a single receiver. Single receiver. Some description is there. So this is Rx. I can write this as TX1 and TX2, two transmitters, right? And it's transmitting to a single receiver. And the channel is given to be AWGN. I have discussed what AWGN is, additive white Gaussian noise, which means that there is no fading. It's just signal and addition of a noise. And total noise power N is, so we know that noise power sigma square is typically some n naught noise spectral density times bandwidth. But essentially, you are just given this noise power sigma square, which is also denoted as capital N. So noise power is given to you as something like 1 milliwatt. You have 1 milliwatt noise in the system, right? And you are told that received power. So at the receiver, you are essentially receiving some You have some receiver. So you are receiving signals of both user 1 and user 2. And for user 1, receive SNR receive power is P1. For user 2, let's say it is P2, right? So you are given the values of P1 and P2. Let's say P1 is 20 milliwatt, P2 is 10 milliwatt. So, and the channel bandwidth is given to be channel bandwidth is given to be 20 megahertz, typical LT value, 20 megahertz, right? And the receiver is safe to, so you are told that receiver decodes TX2. The receiver decodes TX2 first, or TX1 first. Receiver decodes TX1 first. So, TX1 first, right? So you are asked that, okay, you are asked what is the capacity for user 1 with all of this information. So, decodes TX first. So you are asked capacity for user 1 or TX1, whatever. So for capacity, so here there is an interference channel. So we note that here there is interference channel. Why? Because when the receiver is decoding transmitter 1, we have an interfering signal which is coming from transmitter 2, right? User 1 signal is interfered by user 2. So for capacity, I have to use the formula because it's an interference channel. So it's bandwidth times log 2 of 1 plus SINR. So what is SINR? SINR is signal to interference plus noise ratio. So it is P by interference plus noise, signal to interference plus noise ratio. Right. And so for user 1, what is the transmit power? For user 1, the transmit power is 20 milliwatt. And then the noise power is 1 milliwatt, and user 2 signal is interference. So that is 10 milliwatt. So 20 by 11, the answer is how much? I'll just quickly calculate and see. It is 1.8. So this is the value of SINR in linear scale. And so I have to apply this formula. So the question is capacity for user 1. So I know SINR is 1.82. And so I just need to apply this formula, which is 20 times log 2 of 1 plus 1.82 equal to, just quickly do the calculation. 1 second. Into 20. I'm getting something like approximately 29.9 Mbps. So this is a very straightforward question, and this should be easy. So in any, you just have to identify up to which is the actual transmitted signal for user 1, that is P1, and then which is the interfering signal, and then solve. So you'll have more interference channels later. Now, okay, I'm almost at the end of my time, but for the benefit of those who missed the first part, I'm going to go over this really fast because I spent a lot of time. But here, essentially, just for solving problem purpose, you will, if you are not using DFT spreading technique, then you are just, what you will use is this function g of f, which is essentially, this is sinc function in Fourier domain, but in time domain, what you will be doing is for any signal, if you are sampling it, then you will be sampling it over this interval, right? 0 to Ts symbol time. And so in time domain, this is rectangular box, which means in signal domain, it is sinc function, right? And instead of this, so for sinc function, the peak value is Ts, which is a sampling symbol time, and your crossover point, which is when the gain drops, when the like magnitude drops to 0, is when frequency is equal to 1 by Ts. So then you know this crossover point. Now for your chip function, in chip function, what happens is, instead of using that traditional rectangular function, you are taking a smaller rectangular function, 1 by root Ts, with 1 by root Ts gain from 0 to Tc. And then you are shifting this rectangular function by intervals of chip, like by this chip interval, qtc. So you are shifting it by 1 Tc, 2 Tc, etc. So for a total of capital Q chips, or capital Q length of spreading sequence. And so your symbol time Ts is comprising of Q small chips. So this is how you encode it. Ts is equal to qtc, right? And so if you just apply the formula, you will see that if you do the Fourier calculation and all that, it is there in the lecture. You will see that the Fourier transform of this chip function, this is lower, the amplitude is lowered by a factor of q squared, where q is the length of your chip sequence. And the crossing point is, so it becomes flatter, essentially. The amplitude becomes low and it spreads out. So it's the crossing point is multiplied by a factor of q, because sinc function, sinc of 1 is 0. And so essentially at this point, 1 by Tc is nothing but, to solve this, it is q by Ts, right? So it just spreads out and its amplitude reduces. So in your question, you will be asked to do this kind of mathematics, that you have some symbol rate. You'll be given symbol rate. From symbol rate, you can calculate the symbol time, right? Which is 1 by symbol rate. And so from there, you can kind of draw the original, like, if you are not applying spreading, then your this pulse shape will look like this, where you have amplitude as Ts and crossover point is 1 by Ts, which is 1 by 8.125 megahertz. And if you know so how will you calculate Q? You will be provided in question a chip duration, which is Tc. And now you have calculated symbol duration, which is 8 microseconds. So in this case, for this Q factor, you just have to divide symbol duration by chip duration. And so once you know Q factor, you can just divide the amplitude by Q square and multiply the crossover point by Q. And so we get the new spread spectrum, which is amplitude is 0.5 and crossover point here at 0 is 0.5. So it's just, you just flatten it and spread it. That is how you do it. Is this clear?
Sir, how this Q value has come, sir? 4 Ts by Tc?
So symbol time we have calculated to be 8 microseconds, right? So 8 by, and chip time is provided in the question. It was 2. Like I just took the value 2. So you have provided symbol rate, from where you can calculate symbol time, and then you can calculate ratio of symbol time and chip duration. So you will get 4. So this, like, yeah, this is simple calculation. I hope this is clear. Okay. Any more questions? Otherwise, my time is up, and end the session. Yeah, for this, essentially, you just have to calculate symbol time and the rest is just mechanical. Um, okay, fine. Ending the session then. Okay.